Hello everyone! Today I'm going to take a look at the classic oscillator design. This is something you could find in a vintage Moog or Roland from the 70s. You will also see why those designs more or less got completely replaced by integrated circuits, DCOs or other digitally controlled oscillators. Alright, let's get started. So let's take a look at the schematic here. This is a VCO design I came up a few years ago with. So this is nothing really new. You will find something very similar in old synthesizer designs. So let's take a closer look. So this here is the oscillator core. And how this works is actually very simple. We have this capacitor here, and this is charged. And when it's reaching a certain threshold voltage, then it is shorted out with this transistor here. So there's a comparator, and when you reach a certain threshold, then this is shorted out and the cycle starts over again. So this looks basically something like this. So this is here the time, and so the capacitor is charged. And when I reach a certain threshold here, so in this case for Eurorack this is 10 volts, then this is shorted out. And then the cycle starts again. So this is basically generating this source signal here. So, but now it gets a bit more complicated. We don't only want to have this oscillate, but we want to change its frequency, how fast this oscillates, and we want to do this very precisely. So what you see here is exponential current sink. So this is basically a differential amplifier which has a voltage control, and this, with this you can control how much amount of current you can get out of the oscillator core. And by changing the amount of charge that is going into the capacitor, you change the time, how fast it is charged, and subsequently the frequency here. What it makes it so difficult is that this here needs to be very precise. So, but this is doing in the end is you have a control voltage which goes in here. So this is usually 1 volt per octave. So that means you have 1/12 of a volt per semitone, and this is a linear input. So this looks something like this. So you have 1 octave, the next octave, and so on. And this needs to be translated to exponential one, because in every succeeding octave, the frequency doubles. So what we need to do here is we need to convert from linear to exponential. And the problem here is the converter here needs to be very precise because we want to have a good tracking over multiple octaves. So this means we need to stay on this curve here very precisely. And to achieve this in these old designs, you usually use matched transistors here, so they need to be matched very precisely. And what really is an issue here is because we are already at component tolerances, which really was an issue back in the 70s. So what the manufacturers did, they pre-selected components which they put in their synthesizers. But in terms of mass production, this was really a problem. So especially if you want to have this uniform over all your devices that you're selling, and especially if you want to create polyphonic synthesizers. So usually you want to achieve the same sound on every voice, and this is very complicated with this. So what they did in the early 80s, end of the 70s, early 80s, the industry came up with integrated circuits. So this was much easier to achieve a certain quality of this, but this was still an issue to get everything in tune. So this is why they succeeded in the end to digitally controlled oscillators like DCOs, or even fully digital oscillators like wavetable oscillators and so on. So to complete this here, I already talked about temperature issues. So temperature changes will change the properties here of the exponential current sink, and so this is why a good matching is important. And you also see here a thermistor. So this is basically a resistor which is changing resistance on temperature changes. And all this is trying basically to compensate for temperature changes, which works to a certain extent, but not perfectly. So this design here uses an SMD transistors, which are in one package. So this is 2 transistors in one package. The idea behind this is that the transistors are on one silicon wafer, and that they have a very close matching. This works actually pretty well. So I get like a good tracking like this here for over 5 to 6 octaves. So I'm very fine with that. Just to make this complete, so you have basically this is for the scale here. So this is a trim pot for the scale. So this is basically the distance between the nodes, and then as an offset. So this is basically the center point of the oscillator. What makes the whole tuning process of this oscillator a bit cumbersome is that when you change scale, also the offset moves around. So it's a bit of fiddling involved to get this in tune, but if you're a bit patient, then this will work out. So over here, so basically here is the source signal coming out. This is just a buffer, so this needs to be buffered. If you don't buffer this, so this will just break down here. What the capacitor here is doing, so this removes the DC offset which we have here. So this basically moves it to something like this. So you have something like here, plus 5 volts and minus 5 volts. So this is something what you would like to have for an audio signal. Down here, this is creating a pulse signal, and this is also using a comparator. So basically, you have a control voltage going in here. So this basically looks something like this. You have a control voltage, which is, for instance, like 5 volts, something like this here. And what the comparator does, if the signal is below this 5 volts, then it gives you the negative rail of the op amp. So this is something like minus 12 volts in this case, something like this here. And if it's above this 5 volts, then it gives you plus 12 volts rail from the op amp. So this looks basically something like this, and then it goes down here again, and so on. So basically, this gives you this pulse signal here. So what you do to change the pulse width is you can move this control voltage here, and this will change your pulse width in the end here. So it's actually pretty simple. So yeah, that's basically the oscillator core. So I made a Eurorack module out of this. So this is basically all what you see here. On these PCBs in Eurorack format, there is a frequency knob. So this basically is controlling the control voltage which is coming in here. And also fine-tune knob. So this is just changing a bit of the control voltage, and this is basically mixed with the 1 volt per octave input you have frequency modulation. This is basically the same as the CV input here. And so then you have here the saw and the pulse output, as I described. PWM, so this is the control voltage here, and there's a sync signal. What I said in the beginning, so you have these this comparator here, and when it reaches the threshold of 10 volts here, then this is shorted out. And what this is basically doing, you can put another oscillator in here, and then this is tied to the other oscillator. So you can mess around basically with resetting this oscillator. So this is some sort of soft sync, so that gets really nice effects, I would say. Maybe a quick look on the PCB here. So what you can see here is the SMD dual transistor, and I put the thermistor very close to it. So temperature changes hopefully will be cancelled out. Yeah. And here the trim pots. Also you need a precise reference voltage here for the current sink. This is also important, so that can be adjusted here, and trimming for scale and for the offset. And one more thing, so if you're interested in the designs like this, take a look at service manuals from the 70s and the early 80s. So if you're familiar with the basic building blocks from these analog circuits, so you can learn a lot looking into them. I will link some of those in the description. So this is really interesting to look at. Unfortunately, the manufacturers stopped to publish those service manuals, so this is a bit of a pity. Yeah, I guess this was mostly because out of competition, but yeah, very sad. Take a look, this is really interesting. You can learn a lot over there. Alright, that's all for today. So if you're into building synthesizers, make sure to check out my website. So there's a lot of information and schematics over there. I also offer PCBs and kits in Eurorack format, so make sure to check out my shop as well. And yeah, thanks for watching, take care, and see you soon.